Welcome back to this next video in the playlist on Galois theory. So in this video we're going to talk about finite solvable extensions. So we are aiming towards proving that for characteristic zero fields, radical extensions are always contained inside finite solvable extensions, and finite solvable extensions are always contained inside radical extensions. And I said previously that the two key things we're going to need a good understanding of to understand those proofs are Kummer extensions and cyclotomic extensions. I'd like to add a third thing onto that. We need to actually know a little bit more about finite solvable extensions as well, which is the reason I've put this video in, where we're going to explore a little bit more about finite solvable extensions. So for this, I don't think we're going to need our field to necessarily be characteristic zero. I think everything we say here is going to be true for any characteristic. So I'm just going to have a field f then. I'm going to have S be my finite solvable extension of f. And remember what this means. This means that the Galois group of S over f is a solvable group, which means that it will have an ascending chain of normal subgroups where the quotients are all abelians. So if we call our Galois group Gn, it will mean that there will be some chain inside here starting at G0, which is the trivial subgroup, and going up you'll then have G1, and then you carry on all the way up to some Gn minus 1 here, which will be normal inside Gn. And we know that all of these quotients, if you do Gi and you quotient it out by Gi minus 1, that this is abelian. So there exists some chain of subgroups like this inside my Galois group if it's solvable. And we know also that the extension is finite, so this is a finite solvable group. Now what we're going to do is apply Galois correspondence. So Galois correspondence tells us that if we have a finite Galois extension, then there is a one-to-one correspondence between the subgroups of the Galois group and the intermediate subfields between the top and bottom field. So what we're now going to do is find the corresponding subfields, the intermediate subfields, for all of these subgroups in our ascending chain of the Galois group here. So what I'm going to do is, obviously G0 corresponds to S because it is the fixed subfield of S that is fixed by G0, G0 just being the trivial subgroup, so that fixes everything. And then F itself corresponds to the entire Galois group. It's the fixed subfield of the entire Galois group. But then we can, for all the intermediate subgroups, we can now create their corresponding subfields. So we can look at the fixed subfield of S that's fixed by G1. That will be the corresponding subfield to G1. And likewise, we can do this for all of the subgroups here. So it will go all the way up to the fixed subfield of S by Gn minus 1. And then you'll have lots of intermediate subfields here. So there is this ascending chain, therefore, of subfields corresponding to the ascending chain of subgroups, only that the ascension is reversed. So you see, as you ascend in the subgroup here, so the subgroups get bigger, the subfield gets smaller. So the inclusion is reversed in Galois correspondence. So this one corresponds to this one here. Now, what we're going to think about is, what does it mean for the fact we're going to use more advanced Galois correspondence to think, what does it mean that this is a normal subgroup? So we'll start with this one here then, the first subfield just up from F. What does it mean that the subgroup here that it corresponds to is normal in the whole Galois group? Well, of course, this is the Galois group of S over whatever. I don't really want to write its full name out, so let's just call this Fn minus 1 here. So, we're using, I'm assuming you have a good understanding of Galois correspondence and you are aware of this fact that the fixed subfield of S by this subgroup is also equal to the Galois group of S over Fn minus 1. This is the fundamental theorem of Galois theory. This is Galois correspondence. So what does it mean that this is normal inside the whole thing, well, it means that this is going to be a normal extension. It means that this is a normal extension of f. And because it's a sub-extension of the entire extension S, which is finite Galois and is therefore separable, sub-extensions of separable extensions are always separable. Therefore, we get separability easily. Therefore, this is going to be a finite Galois extension. So that's what we're overall concluding. From the fact that this is a normal subgroup, we can conclude that the corresponding extension for it is a finite Galois extension. And what's the Galois group of this finite Galois extension going from F to this one here? Well, it's the quotient of this one by this one, which we know is abelian. So what we actually know is that this is a finite abelian extension, is what we're concluding here. And now actually you can continue this on, because now if I go up to the next one, which we could call Fn minus 2 here, corresponding to Gn minus 2, well, again, you can do exactly the same thing. So you can say it is going to be a finite Galois extension of Fn minus 1 because of the fact that this one here, Gn minus 2, is normal inside Gn minus 1. And again, its Galois group is going to be Gn minus 1 quotiented out by Gn minus 2, which is going to be abelian. And therefore, we can conclude this is a finite abelian extension. And you can go on. You can conclude, basically, that all of these extensions that we've built here are finite abelian extensions. So what actually I've been able to conclude is that if I've got a finite solvable extension, it is actually built out of a whole bunch of finite abelian extensions. Good. Now, what I want to ask is, does it go the other way around? So if I've got finite solvable, I'm able to conclude that it's built out of a finite tower of finite abelian extensions. So I'll abbreviate that to this, FTFAA, because I just don't want to have to write it all out. So finite solvable implies that it's built out of a finite tower of finite abelian extensions. Does the other way round hold true, is the question. If I have an extension that is built out of a finite tower of finite abelian extensions, can I then conclude that my overall extension is finite solvable? Well, the answer is no, and the reason is that you're not even sure that the whole extension is going to be finite Galois. And remember, to be finite solvable, it certainly has to be finite Galois. So you can't conclude that necessarily. However, if you have the fact that it's built out of a finite tower of finite abelian extensions and it's finite Galois, then it holds. Then you can conclude it's finite solvable. So let me show you this. So if we have our extension, so let's just call it K, and let's say it's built out of this tower of extensions, so let's call it, so we'll call K Kn, and then let's say we've got Kn minus 1, Kn minus 2, all the way down to, and then you get to K1 and K0, which we'll call F. So this is our extension here. We're saying that we know the entire thing is finite Galois. So Kn over K0 is finite Galois. And we're saying that every single one of these individual extensions here is an abelian extension, so finite abelian. So meaning it's Galois with an abelian Galois group. And then I'm claiming that I can now conclude that this extension is then a finite solvable extension. Whereas what I said before is that if I don't know this bit, if I don't know it's finite Galois, if I just build a tower of abelian extensions, then it's not the case that the whole thing will necessarily be finite solvable, because it's not the case that the whole thing will necessarily be finite Galois. And you should be able to cook up easy examples, easy counterexamples where you can build a abelian extension on top of an abelian extension, and it doesn't make overall an extension that is finite Galois. I won't embarrass myself by trying to come up with one on the spot, but I know it's not difficult. In the majority, if you build an abelian extension and put another one on top of it, come up with any example you like, it's more likely than not that the whole thing will not be finite Galois. If you manage to cook up one that is finite Galois, then you've done well. So it's not difficult to cook up examples. So However, if the whole thing is finite Galois and it's built out of a tower of finite abelian extensions, can I conclude the whole thing is finite solvable? The answer is yes. Why, then, is the question. So it's because so we know the whole thing is finite Galois, so it will have a Galois group, so call it the Galois group of Kn over K0. And now we apply Galois correspondence again. So I'm going to actually, this needs to be down here actually. So we need Galois group of Kn over K0 to be down there here. And then up here will be the Galois group of Kn over Km, which is just the trivial subgroup. And then Galois correspondence now holds. These are all intermediate subfields, these things here. So they will have corresponding subgroups of the Galois group, which will be their Galois group. So we can take Galois group of Kn over Kn minus 1, and that'll be a subgroup. And then we can do Galois group of Kn over Kn minus 2, and that will be a subgroup. And these will correspond beautifully to the subfields here, because I know the extension is finite Galois, and therefore Galois correspondence holds. And then K1 will have its Galois group, the Galois group of Kn over K1, and that will be here. So we'll have this correspondence here. Now, because I know, so let's start down here with K1. Because I know that this is an abelian extension here, it's certainly finite Galois. So that means that this subgroup, Kn over K1, the Galois group of Kn over K1, this must be normal inside the Galois group of Kn, K0. That's because this is a finite Galois extension. Moreover, because it's an abelian extension, I know that the Galois group of it is going to be the quotient of these two. It's going to be Gal Kn over K0, quotiented out by the Galois group of Kn over K1, and therefore I know that this quotient here has to be abelian. And then I just carry on. So if I go up to K2 now, again, because K2 is an abelian extension of K1, I can therefore conclude that the Galois group of Kn over K2 has to be a normal subgroup of the Galois group of Kn over K1. And because it's abelian, I can conclude that the quotient has to be abelian. And then this just continues. Basically, this chain has to be a chain of normal subgroups, and the quotients are all going to have to be abelian. And therefore, I can conclude that the Galois group of Kn over K0 is solvable, because here is my ascending chain of normal subgroups with abelian quotients. So that's how you prove then the other side of this, which is that if I know the overall extension is finite Galois, and I know it's built out of a finite tower of finite abelian extensions, then I can conclude the overall extension is finite solvable. Excellent. So that gives us this sort of a better understanding of what finite solvable extensions are. Finite solvable means that it's finite Galois and it's built out of a finite tower of finite abelian extensions. Similarly, the other way round holds. If it's finite Galois and built out of a finite tower of finite abelian extensions, then I can conclude it's finite solvable. I want to just go one little step further, which is something we're going to use later, which is actually extend this if and only if here. So I can now take out that question mark. I know that this is true, so I'll put a box around these. You need both of those conditions. And now I'm going to add another if and only if here, which is that it's going to be finite Galois and built out of a finite tower of finite abelian extensions if and only if it's finite Galois and built out of a finite tower of finite cyclic extensions. So I can refine it to cyclic. Now, one direction of this is obvious. If it's true that it's built out of, if the overall extension is finite Galois and it's built out of a finite tower of finite cyclic extensions, well, cyclic extensions are all abelian. Therefore, it's certainly going to be the case that it's built out of a finite tower of finite abelian extensions. So this one, this direction, this backwards direction here is obvious. The forwards direction needs a little bit of work. Why, if it's the case that it's built out of a finite tower of finite abelian extensions, does it mean that it's built out of a finite tower of finite cyclic extensions? So we go back down to our picture here. Here is our extension that's built out of a finite tower of finite abelian extensions, and the overall thing is finite Galois. How can I now conclude that it's built out of a finite tower of cyclic extensions? Well, all I need to do is prove that one of these abelian extensions can be split up into a finite tower of cyclic extensions, because then if I do that, then it will be the case that all of them can be split into a finite tower of cyclic extensions, and then I'll just be able to split each one of them into their finite tower of cyclic extensions. You know, I might have to add in a few sub-steps here, but I'll be able to do that for each one, and then I'll overall have this huge, great finite tower of cyclic extensions. So overall, all I need to do is, if I have an extension k over f, which is a finite abelian extension, I want to prove that there exists a chain inside here of sub-extensions which are all cyclic. So let's do this. So take the Galois group then of k over f. I know it has a Galois group because it's an abelian extension, therefore it's a finite Galois extension. Or rather, I know it's a finite abelian extension, therefore I know it's a finite Galois extension. So here is its Galois group, and its Galois group is abelian. So we're now going to use a theorem from group theory called the fundamental theorem of finite abelian groups, which says that any abelian group is isomorphic to a product of cyclic groups. So this Galois group, therefore, because it's abelian, it is isomorphic to some product Cn1 cross Cn2 cross all the way up to Cnk, where I don't know what these n1, n2, nks are. They're all just natural numbers, but we don't know what they are. They could be anything potentially. So that's the fundamental theorem of finite abelian groups. It tells me that my abelian group is isomorphic to a product of cyclic groups. I'm not going to prove the fundamental theorem of finite abelian groups. I'm going to assume you know it. It can be proven reasonably easily just applying an inductive type argument and using Cauchy's theorem. Just to sort of say briefly how you would sort of think about proving this in case you don't know how to prove it, so you can think about it. You know, take your abelian group, take the cardinality of it, take its prime factorization, take one of the prime factors that appears in its prime factorization, apply Cauchy's theorem with that to get an element of that order, then take the subgroup generated by that element, and then that subgroup will be normal in your group because the whole group's abelian and therefore all subgroups are normal. Quotient out by it, you'll then get a quotient group of smaller cardinality, apply the inductive hypothesis to say this is now isomorphic to a product of cyclic groups, and then think about the quotienting that you've done and think about how you can go back up, lift it up to the entire group, and how your isomorphism of the quotient group is then going to become an isomorphism of the whole group, where you just now need to add on an extra direct product with the cyclic group of cardinality, whatever prime it was that you found an element of that order to quotient out the cyclic group generated by. That's the sort of sketch of how you would prove it. That's the sort of easy way to prove it. Sort of the cheating way to prove it. Well, not a cheating way, the more general way to prove it, which requires a lot more effort, is to prove a much, much bigger theorem in module theory called the structural theorem of finitely generated modules over PIDs, because that then implies a more general theorem called the fundamental theorem of finitely generated abelian groups, which certainly then implies the fundamental theorem of finite abelian groups. So those are sort of kind of two ways that you would prove it. If you're sophisticated, you would do it using the module theory structure theorem, the great structure theorem, probably the most important theorem in all of module theory and commutative algebra. If you haven't done that sort of level of algebra, then there's a way of proving it just with group theory. Anyway, we're not going to do either. We're going to just use it. So what does this now mean? This means that my abelian group, it's actually going to have an ascending chain of subgroups that are all going to be normal because it's abelian and therefore all subgroups are normal. and where the quotients are going to be abelian, going to be cyclic, because look at this. If you have your group, which is this, it's this product of cyclic groups, you can now take the subgroup, which is Cn1, and you can then take the subgroup Cn1 cross Cn2, and you can then go higher to the subgroup, which is Cn1 cross Cn2 cross Cn3, and you can keep going all the way up to the whole thing. So you can create this ascending chain of subgroups where you're just adding on an additional product each time. And now each one, Cn1 is going to be normal inside Cn1 cross Cn2 because they're all abelian and therefore all subgroups are normal. And what's the quotient going to be? You might need to think about this a little bit, but the quotient is going to be Cn2. Because, if we think about this, like, when we think about Cn1 cross Cn2, I mean, it's kind of, the notation is incredibly suggestive. If you quotient out by Cn1, it's kind of obvious from the notation that you're going to get Cn2. But why actually thinking about this more does that work? Because the elements of this product here are going to be pairs of elements, where the element here in the first position comes from the first one here, and the second one comes in the second position comes from this one here. And the subgroup that we are quotienting out by is the subgroup of all elements that appear like this, where they've got the identity for the second one, which I'll call 0, in the second position, and then you let A1 vary over all the elements here. That's the subgroup that I'm quotienting out by. And when I do that, what are my cosets going to look like? Well, the cosets are going to contain the elements that have all the different entries. So if I draw a picture, so like, here's my subgroup. This is my Cm1 subgroup consisting of, let's do a concrete example. So let's do C2 cross C3. Then we'd have 0, 0 here, and then we'd have 1, 0 here. This is my subgroup of C2. And then my cosets are going to be 0, and then we're going to have 0, 1, which is going to be an element in this group. And now think what its coset is going to be. Well, if I compose it with 0, 0, I just get itself back again. If I compose it with 1, 0, I would get 1, 1. So I get all the possible entries here where you have 1 in the second thing, and then finally we would have 0, 2 up here, and then again, if I compose it with 0, 0, I just get itself back again, and then if I compose it with 1, 0, I would get 1, 2. So what I'm trying to convince you of is that actually the cosets are, the things that are in the same coset are always going to have the same entry in their second position, and therefore you can see therefore that when we quotient out and now build the group that is made out of these cosets here, it's going to be the same as C3. It's going to be the same as if you just discount what's in the first position and just look at what's in the second position, these things, and compose them together in that second thing. So this works quite nicely. And then going on, if I go up from Cn1 cross Cn2 to Cn1, hopefully you can still see this. So if I go now up from Cm1 cross Cn2 to Cm1 cross Cn2 cross Cn3, again, this one is going to be normal in this one, and when I quotient out by this one, it's going to give me Cn3. So what I'm overall arguing is that my abelian group has this ascending chain of subgroups in it, where each of the quotients, firstly, all of the subgroups are normal in one another, but all of the quotients are cyclic as well. And this holds for any abelian group. So what I can now do is apply this here and then apply Galois theory. So I'm going to have, inside my Galois group, my abelian Galois group, I'm going to have this chain of normal subgroups. So we'll call our Galois group Gn again. And now I've got this chain of normal subgroups where all of these quotients that you get here give cyclic groups. And now what I can do is find their corresponding subfields over here, and because they're all normal in one another, all of the extensions are going to be finite Galois extensions. We've already seen that. and because the quotients are cyclic, that means all of these Galois groups are going to end up being cyclic. So it means that my finite abelian extension is actually necessarily made up of an ascending chain of finite cyclic extensions. So now I just go back up here to where I've got my finite Galois extension built out of a finite number of abelian extensions, and I just split all of these abelian extensions up into their intermediate cyclic extensions. I do it for every single one of them, and then I've overall built the entire extension out of a finite tower of finite cyclic extensions. So that then proves this direction here of this if and only if statement here. If I've got a finite Galois extension built out of a finite tower of finite abelian extensions, I can conclude that it's built out of a finite tower of finite cyclic extensions. And we will need this at some point. We will need, because we've got an if and only if here and an if and only if here, I've now therefore got an if and only if between these two as well. So if I've got a finite Galois extension that is built out of a finite tower of finite cyclic extensions, I can conclude it's finite solvable. If I've got a finite Galois extension that's built out of a finite tower of finite abelian extensions, I can also conclude it's finite solvable, etc. So we will use this in our proof. So remember this. So we'll end there. Thank you very much for watching. Sorry about this. Oops, what on earth have I just done? Bear with me.